Welcome learners to this session on aldehydes and ketones part 2. In aldehydes and ketones part 1, you have studied about the structure and preparation of aldehydes and ketones, and in this session you will learn about the physical properties of aldehydes and ketones, their chemical reactions and the uses of aldehydes and ketones. The learning outcomes expected from this session are to explain the physical properties of aldehydes and ketones, describe the chemical reactions of aldehydes and ketones, and discuss the uses of aldehydes and ketones. So, let us start with the physical properties of aldehydes and ketones. Methanol is a gas while ethanol is a volatile liquid at room temperature. The other aldehydes and ketones are liquids or solids at room temperature. They have the dipole-dipole interactions between their molecules, and that is why there is a weak molecular association between the molecules, and this results in their higher boiling points as compared to the hydrocarbons or the ethers of comparable molecular masses. For example, the boiling point of propanol is 322 Kelvin and that of acetone is 329 Kelvin. Both of them have a molecular mass of 58, and normal butane having the molecular mass 58 has a boiling point of 273 Kelvin, and the ether methoxymethane has a molecular mass of 60 and has a boiling point of 281 Kelvin. You can see that there is a table containing the boiling points mentioning these trends, but their boiling points are lower than the corresponding alcohols of similar molecular masses, because alcohols have intermolecular hydrogen bonding between their molecules, which is absent in aldehydes and ketones. Hence, the boiling point of propane 1-ol, that is molecular mass 60, is higher than the propanol, which has a boiling point of 322 Kelvin as compared to 370 Kelvin of propane 1-ol, because of the hydrogen bonding only, and acetone has a boiling point of 329 Kelvin, and both of these have a molecular mass of 58. The third physical property is about their miscibility. The lower members, that is methanol, ethanol and propanone, are miscible with water in all proportions, as these form hydrogen bonds with water. You can see the hydrogen bonds are denoted here by dotted lines in the figure. With the increase in the length of the alkyl chain, the solubility decreases because the hydrophobic part has increased in the molecule. All aldehydes and ketones are fairly soluble in organic solvents like benzene, ether, ethanol, methanol, etc. Lower aldehydes have sharp pungent odors. With the increase in the size of the molecule, the odor becomes less pungent but more fragrant, and that is why many naturally occurring aldehydes and ketones are used in perfumes and flavoring agents. So, after understanding their physical properties, let us now study the chemical reactions of aldehydes and ketones. The chemical reactions of aldehydes and ketones can be categorized as nucleophilic addition reactions, reduction reactions, oxidation reactions, reactions due to alpha hydrogen and other reactions. So, let us first start with the nucleophilic addition reactions. We will first consider the general nature or the mechanism of this reaction. In the carbonyl group, the carbon atom is electropositive while the oxygen atom is electronegative. That means, one is electrophilic, the other is nucleophilic. So, a nucleophile now can attack to the electrophilic carbon from a direction which is approximately perpendicular to the plane of the sp2 hybridized carbon of the carbonyl group. So, in the first step, which is the slow step of the reaction mechanism, the hybridization of the carbon changes from sp2 to sp3 and the tetrahedral intermediate is obtained in this step. You can see here in the figure that in the second step, this tetrahedral intermediate captures a proton from the reaction medium to give a neutral addition product, and the second step of this reaction mechanism is fast. Thus, in the nucleophilic addition, the nucleophile, that is Nu negative and H plus, add across the carbonyl double bond. At this stage, you may be curious to know about the relative reactivities of aldehydes and ketones, that is, which one is more reactive. So, let us understand that about the reactivities of aldehydes and ketones. Aldehydes are less sterically hindered than ketones, because in aldehydes one alkyl and one hydrogen is present at the carbonyl carbon, whereas in ketones the two alkyl or aryl groups are attached to the carbonyl carbon. Thus, due to steric reasons, ketones are less reactive than aldehydes in nucleophilic addition reactions. Also, there is an electronic reason for the lower reactivity of ketones. What is that? Let us understand that. The two alkyl groups present in the ketone reduce the electrophilicity of the carbon atom of the carbonyl group. The alkyl groups, you know, are electron donating in nature and they are having plus I effect as compared to the single alkyl or hydrogen present in the case of aldehyde. So, definitely now ketones are less reactive both due to steric reasons as well as electronic reasons. Let us now consider a variety of compounds which result from these nucleophilic addition reactions. We will consider the examples of nucleophilic reactions and then nucleophilic addition elimination reactions as well. The first reaction is addition of hydrogen cyanide, that is HCN, and here the addition of HCN to aldehydes and ketones give us cyanohydrins. This reaction is slow with pure HCN and is catalyzed by the use of a base which gives us cyanide ion, which is a more stronger nucleophile than HCN. The mechanism of the reaction is shown here. You can see that first we get a tetrahedral intermediate and then finally the cyanohydrin. The cyanohydrins obtained are very useful synthetic intermediates and can be further converted to many other compounds. The second reaction is addition of sodium hydrogen sulfite. Sodium hydrogen sulfite reacts with aldehydes and ketones to form the addition products, and the resulting products are crystalline compounds obtained are water soluble and can be converted back to the carbonyl compounds by treating them with dilute mineral acid or alkali. This serves now as a useful addition product which has been obtained by the addition of sodium bisulfite, because you can use this as a purification tool of aldehydes and ketones. The next reaction is also very interesting and it is the addition of Grignard reagents. The nucleophilic addition of Grignard reagent, that is RMJX, to the carbonyl compound forms adduct first, and then by hydrolysis of this adduct you get alcohols. Very, very interesting reactions. And if we start with formaldehyde or methanol, then you will be getting primary alcohol. You can see in this reaction, and if you start the reaction with other aldehydes, you will be getting a secondary alcohol, while if you start with a ketone as the starting material and react it with Grignard reagent, finally you will obtain a tertiary alcohol as a product. So, all the three you can get from this reaction: primary, secondary and tertiary alcohols. Now, the fourth reaction is now addition of alcohols. Aldehydes react with one equivalent of monohydric alcohols in the presence of hydrogen chloride to give a hemiacetal, that is alkoxy alcohol. intermediate which further reacts with the one more molecule of alcohol to give a gem acetal. Mind the word gem acetal, which is a gem dialkoxy compound. Here gem means that both the alkoxy groups are attached to the same carbon atom, as you can see in this reaction also. Similarly, ketones react with alcohols to give a hemiketal or the ketal after reacting with the second molecule. But if the starting material is ethylene glycol, you can see how the two OH groups present in the same reactant molecule react given in this reaction. The dry HCl here protonates the oxygen of the carbonyl group and increases its electrophilicity. How? Because of the protonation. You can see in this structure how this protonation increases the electrophilicity of the carbonyl group, that is specifically carbonyl carbon, which facilitates the attack by the nucleophile on this carbon. Since the acetal and the ketal formation are equilibrium reactions, addition of aqueous mineral acid converts acetals or ketals back to the carbonyl compounds. We will next consider the addition of ammonia and its derivatives to the carbonyl group. The general reaction can be represented as shown here. Here you can see that Z can be a variety of groups, that is, it is H if we are using ammonia, and it can be now aryl group, OH, NH2, C6NH group, or even the dinitro compounds also, and also NHCONH2. So, this can be the variety of the Z which is attached to the furthermore hydrogen atom, and the reaction is again a reversible reaction and is acid catalyzed reaction. And if we follow it by the dehydration, then we will be getting the addition elimination products. You can see in the table that by changing the Z group in the reactant, we can get an amine, a substituted amine, then we can get an oxime, phenylhydrazine. If we start with, we will be getting phenylhydrazone, then 2,4-dinitrophenylhydrazone also, and then semicarbazone also if we start with semicarbazide. So, these are wide variety of products you can get by this reaction, and since it is the reaction of sort of addition elimination, we are getting these products. We will now consider the reduction reactions of aldehydes and ketones. We will first consider the reduction to alcohols. Aldehydes can be reduced to primary alcohols and ketones can be reduced to secondary alcohols, and what reagents you can use for this purpose? These are sodium borohydride, that is NaBH4, or lithium aluminium hydride, that is LiAlH4, and also you can do this process by catalytic hydrogenation using finely divided platinum, palladium or nickel catalysts, and the reaction is shown here. Then we can also reduce carbonyl compounds to the hydrocarbons. The carbonyl group of aldehydes and ketones can be reduced to CH2 group by again two methods, which is Clemmensen reduction or by Wolff-Kishner reduction. The reaction conditions are different. The Clemmensen reduction uses zinc amalgam and concentrated hydrochloric acid, whereas Wolff-Kishner reduction uses hydrazine followed by heating with sodium hydroxide or potassium hydroxide in high boiling solvents such as ethylene glycol. Next, the opposite to the reduction is oxidation. So, we will consider oxidation reactions. Aldehydes are easily oxidized to carboxylic acids, while ketones under vigorous conditions using strong oxidizing agents and high temperatures undergo oxidation. For aldehydes, we can use common oxidizing agents such as nitric acid, potassium permanganate, potassium dichromate, and even mild oxidizing agents such as Tollens reagent and failing reagent also. And we will now consider the reactions with tolerance reagent and failing solution. The oxidation of ketones involves the breaking of CC bond, and we will get a mixture of carboxylic acids, as you can see in the equation here. We are getting even the products which contain lesser number of carbon atoms than the starting parent ketone. The aldehydes and ketones can be distinguished by using tolerance test and failings test. Let us see first what is tolerance test. Tolerance reagent is freshly prepared ammoniacal silver nitrate solution which has the AgNH2 plus ions, and aldehydes on warming with this reagent produce a bright silver mirror on the walls of the test tube when we perform this test. Now, as the aldehydes are converted to carboxylic acids in this reaction, and we are doing the reaction in the alkaline medium, we are getting now carboxylate ion as the product and not the carboxylic acid, and the reaction involved is shown here. The second test for distinction of aldehydes and ketones is failings test, and failing reagent contains two reagents. One is failing solution A and the second is failing solution B, which are mixed in equal amounts. So, let us see what is failing solution A. It is an aqueous solution of copper sulphate, and failing solution B is alkaline sodium potassium tartrate, which is also known as Rochele's salt. So, these two solutions are mixed in equal amounts to get the failing reagent. Aldehydes on heating with failing reagent give a reddish brown precipitate of copper oxide, and again the aldehyde group is oxidized in this reaction to the carboxylate ion, you can see here in this reaction, but aromatic aldehydes do not give this test. The next reaction we will be considering is oxidation of methyl ketones. Aldehydes and ketones having at least one methyl group attached to the carbonyl carbon are oxidized by sodium hypohalite to the sodium salt of the corresponding carboxylic acid, which is having one carbon less than the starting carbonyl compound. And if you use chlorine, bromine and iodine instead of X, which we have said, we will get a halo form in the product accordingly. And the methyl group which was attached gets converted to the halo form. And if we use sodium hypoiodide, then we are getting iodoform, that is CHI3 as the product, and this is used as a test for the detection of CH3CO group or any other group like this which is having a hydroxyl group attached to the CH group, which is further attached to the methyl, which is now on oxidation again converted back to the CH3CO group. Those kinds of groups also will give this positive iodoform test. Iodoform is a yellow crystalline compound. If the carbon-carbon double bond is present in this reaction in the molecule, it is not affected by this test. You can see an example of this kind of a molecule also in this reaction. We will now focus our attention to the reactions of alpha hydrogen, which are very interesting reactions of aldehydes and ketones. The hydrogen which is attached to the carbonyl group, that means attached to the carbon which is further attached to the carbonyl group, are acidic in nature due to strong electron withdrawing effect of the carbonyl group, and the resonance stabilization of the conjugate base is there as shown here. Aldehydes and ketones can undergo aldol condensation reactions, and now we will be considering aldol condensation in detail. The aldehydes and ketones with at least one alpha hydrogen in the presence of the alkali as a catalyst form beta hydroxyaldehydes, which is called aldol, or if we are using a ketone then we are getting beta hydroxy ketones as the products which are called ketals. This is now called aldol reaction, and we can see the wide variety of products which are obtained if we use the different starting materials in this reaction. The name aldol comes from the words aldehyde and alcohol functional groups which are present in the product. ALD from the aldehyde and OL from the alcohol. The aldol and the ketol now can lose water, and we can get the condensation products from the aldol or the ketol. And now this reaction will be known as aldol condensation. Even for ketones, the same name is retained because of the similarity. And you must be now curious to know, if the starting aldehydes are different, what will happen? Then we call this reaction as a cross aldol condensation. And if we start with two different aldehydes, as the reaction is shown in the following structure, or even with the two different ketones, or if one aldehyde and one ketone, then we will be getting different cross aldol condensation products. If we specifically take ethanol and propanol as the starting aldehydes, then we will be getting the mixture of the following four products, and here two products are from the self condensation of the two aldehydes, that is ethanol and propanol, and two products are from the cross condensation of the two aldehydes. So, let us now see the cross aldol condensation of a aldehyde and a ketone also, which is given in this reaction. One more interesting reaction about aldehydes is Cannizzaro reaction, one more name reaction you can say, and here it is shown by those aldehydes which do not have alpha hydrogen. See, aldol condensation was given by those aldehydes which had alpha hydrogen. Now, Cannizzaro reaction is shown by those aldehydes which do not have a alpha hydrogen, and here the aldehyde undergoes self oxidation and reduction. That means disproportionation is happening, and we are getting this reaction in the presence of a concentrated alkali, not the dilute alkali. So, here one molecule of the aldehyde gets reduced to an alcohol, while the other molecule is getting oxidized to the carboxylic acid, and since the medium is alkaline, we are getting a carboxylate salt in the product. You can see the reactions here. The next reaction is now for aromatic aldehydes, where a benzene ring is also present in the addition to the CHO group. The aromatic aldehydes or ketones undergo electrophilic substitution reactions just like with other aromatic compounds, and here the carbonyl group is acting as a meta-directing deactivating group, and one such reaction is shown here for benzaldehyde. You can see where we are getting from benzaldehyde, if we are starting, then meta-directing CHO group directs the incoming nitro group to give the meta nitro benzaldehyde as a product. So, having seen this wide variety of reactions which are exhibited by aldehydes and ketones, let us now have a glimpse of the uses of the aldehydes and ketones. Aldehydes and ketones are used in chemical industry as solvents, starting materials, and reagents for synthesis of other products. Specifically, formaldehyde is used as formalin also, 40% solution, to preserve the biological specimens in the biological labs and other places. Formaldehyde used to prepare bakelite, which is a important phenol formaldehyde resin, and urea formaldehyde resin and other polymeric products. Similarly, acetaldehyde is used as a starting material for the manufacture of acetic acid, ethyl acetate, vinyl acetate, and other polymers. And also drugs are also not area which is untouched by the use of aldehydes. Benzaldehyde is used in the perfumery and dye industry. Acetone and ethyl methyl ketone are industrial solvents, and butyraldehyde, vanillin and acetophenone and camphor are very well known compounds used as flavors. So, let us now sum up what we have learnt in this session. Aldehydes and ketones are very important compounds and they have a wide variety of uses. The physical properties of aldehydes and ketones can be related to their structural features. Aldehydes and ketones exhibit the following category of important reactions, that is nucleophilic addition reactions, nucleophilic addition elimination reactions, reduction, oxidation, and then electrophilic substitution again where aromatic ring is present. Then reactions due to alpha hydrogen where we studied aldol condensation and cross aldol condensation. Then Cannizzaro reaction which is exhibited by aldehydes which do not have alpha hydrogen atom. After understanding the interesting reactions of aldehydes and ketones, now there are some questions for you to answer. Write the mechanism of ketal formation. How does sodium borohydride or lithium aluminum hydride act as reducing agent? Find out the mechanism for Cannizzaro reaction, very important reaction you just studied. Find out the structures of various polymers formed by formaldehyde. And now let us sum up what we have learnt in this session. Aldehydes and ketones are very important compounds and have a variety of uses. The physical properties of aldehydes and ketones can be correlated with their structural features. Aldehydes and ketones exhibit the following reactions: nucleophilic addition reactions, nucleophilic addition elimination reactions, reduction, oxidation, then reactions due to alpha hydrogen atom which are aldol condensation and cross aldol condensation. Cannizzaro reaction which is exhibited by aldehydes which do not have alpha hydrogen atom. Lastly, we studied electrophilic substitution in case of aromatic aldehydes and ketones. We hope you enjoyed learning in this session. Thank you very much.